Okay, so geometric sequences are sequences which have a first term and then a common ratio. So instead of having a common difference, like last time, it's multiplied by r, which is what we call the common ratio to get from one term to the next. A is still our first term. So our next term, we multiply by r, so we get AR squared. And the next term then is AR cubed, etc. So the nth term, which we will describe as UN, like we have in the past. So UN equals AR, and just like with the arithmetic sequences, we add n minus 1 term. So here it's AR to the n minus 1 for the nth term. Okay, so that is the nth term of a geometric nth term of a geometric sequence. And now if we want to add up the terms of the sequence, so in other words we find the series, we've got to be able to work that out. So Sn, the sum of the first n terms, is equal to the first term plus the second term plus the third term plus etc etc up to ARn minus 2 plus ARn minus 1. That would be the last term of the sequence. So we now need to multiply, and we're going to multiply Sn by r. So in terms of remembering the proof, we multiply by r, so we get Rsn equals, multiplying a by r gives us AR, multiplying AR gives us AR squared plus AR to the n minus 2. If we multiply AR to the n minus 2 by r, we get AR to the n minus 1, and our last term will be AR to the n. Okay, now you've probably noticed that as I've done that and the way I've written it out, that these line up. So AR lines up with AR, AR squared with AR squared, AR to the n minus 2, AR to the n minus 2, etc. Right? So they've all lined up in pairs. So I can eliminate nearly all of these terms if I subtract. So multiply by r, and then we subtract. So if we subtract, we get Sn minus Rsn is equal to A minus AR to the n. Factorise. And factorising, we get A lots of 1 minus r to the n. And over here we've got 1 minus r times Sn. So the sum of the first n terms of a geometric progression is equal to A lots of 1 minus r to the n over 1 minus r. So that's the sum of the first n terms, and that proof you must learn. Learn proof. It's a requirement in specification. Okay, it's not optional. It's highly like one of these kind of proofs is going to be assessed, so you need to learn them. Okay, now the other thing which is interesting about this is what happens if we sum to infinity. And that doesn't, before I do that, we're going to just say that this is the best form to learn, provided the modulus of r is less than 1. If the modulus of r is greater than 1, we often write it as a lots of r to the n minus 1 over r minus 1, provided, or use when the modulus of r is greater than 1. So we tend to use that version if r is bigger than 1, because r to the n then, this term is getting bigger and bigger and bigger, and this makes the top here positive. If r is greater than 1, this is positive. If r is less than 1, this is positive. R to the n, if r is less than 1, is less than 1. So this whole thing is positive. So that's why we tend to use them that way round. Okay, now, as n tends to infinity, Rn tends to 0, provided the modulus of r is less than 1. Just take your calculator, take a number like 0.5 and square it, and then square it again and square it again, and keep on going. And you notice that the value of is going down and down and down and down. So as n gets large, the number of terms in the sequence increases, then the value of Rn gets lower and lower and lower. It tends towards 0, provided the common ratio is less than 1. Okay, so therefore Sn tends to a over 1 minus nothing, which is 1, so a times 1 is 1, over 1 minus r. So the sum to infinity is equal to a over 1 minus r. And again, you need to learn not sure what's happening here. Learn that result. Okay. Now, I've covered there the sort of the factual information that you need for the next 3 or 4 sections of work. Please make sure you've got those written down and that you learn the proof and the 3 results.